Polar coordinates. Before we talk about the polar coordinate system, let's review the Cartesian coordinate system. The Cartesian coordinate system is the coordinate system that we've been using thus far in this course. So this is your typical x-axis and y-axis, and when you go to locate a point P in the plane, it will correspond to some value x on the x-axis, and it will correspond to some value y on the y-axis. And this is sometimes called the rectangular coordinate system. And we call it this because when you line up the x-coordinate and the y-coordinate on the corresponding axes, you can see that it creates a rectangle. Now, the polar coordinate system is another system for locating a point P in the plane, except now we only have one reference here, and that is to the polar axis. So the way that we locate a point in the plane is we first measure the distance from the polar axis, and this distance is called r, and then the angle that is made between this line and the polar axis is called theta, and the coordinates are given as r and theta. Both of these systems have advantages and disadvantages. For example, in the polar coordinate system, these points do not have a unique representation, and this is because if I have an angle theta, for example, we know that if we take that same angle theta and we add a full 2 pi to that, we will end up at the same location. So there is not a unique representation of this point in polar coordinates. In the Cartesian coordinate system, this representation for this point, x and y, is unique. There is only one x value on the x-axis corresponding to this point, and there is only one y value on the y-axis corresponding to this point. Now, the fact that we have unique representations in the Cartesian coordinate system is both a strength and a weakness, and the same thing is true about the polar coordinate system. The fact that these points do not have a unique representation is both a strength and a weakness. So this system does not replace the Cartesian coordinate system, it gives us options. In our first example, let's simply learn how to plot points in the polar coordinate system. And for this, I've brought in a polar coordinate graph where you can see the polar axis is here. And then on this graph, we have some of our important angles highlighted here. And we also have these concentric circles, which will help us measure how far out to travel when we go to a particular point. So for example, our first point is 5 pi over 4. Now the way to graph these is you first want to go to the angle. So 5 pi over 4 is this angle down here. And now along that line, we are going to travel a distance of 1 unit from the origin. By the way, the origin here is called the pole in the polar coordinate system. So if we travel 1 unit, you can see that that 1 unit will be right here. And so this is the point A. So we'll call this point A. The next point to graph is the point 3 pi. So again, I'm going to go to the angle 3 pi first. So if I'm on the polar axis here, we know that if we go 1 pi, that takes us over to here. 2 pi takes us back around to here. And 3 pi is going to put us back over here again. So the angle 3 pi is this angle right here. And we are going to travel 2 units in that direction. So that's going to put us right here, and we'll call this point B. Now our next point is, again, r equals 2, but now the angle is negative 2 pi over 3. So we're going to go to the angle first. So starting at our polar axis here, Negative 1 pi over 3 would be to here, and negative 2 pi over 3 would be to here. So please understand that negative 2 pi over 3 and 4 pi over 3 are equivalent. They're not equal, but they are equivalent because they are coterminal angles. They end up in the same spot. So negative 2 pi over 3, again, is this angle here. And now we are going to travel a distance of 2 units in that direction. And so this will be point C. And finally, we have the polar coordinates negative 3 and 3 pi over 4. So 3 pi over 4, that's easy enough to find. So on our polar axis, 1 pi over 4 is here, 2 pi over 4 is here, and 3 pi over 4 is this angle right here. And then once again, we are going to go a distance of, it says negative 3. Well, if it was 3 units, we would go 3 units. But negative 3, what does that mean? Well, it means the only thing that it could possibly mean, and that is you are going to travel in the opposite direction. So what we have to end up doing is drawing the angle that is 180 degrees from 3 pi over 4, which is this angle here, and then we're going to go 3 units in that direction, and this will be point D. So we can deal with a negative value for r by simply going to the original angle and then going literally 180 degrees in the other direction. There is, of course, a relationship between polar and Cartesian coordinates. So if we have a point in the plane, you can see that this has a Cartesian coordinate of x and y, where x and y correspond to the values on the x and y axis. And then, of course, we have r, which is the distance from the origin or from the pole to the point P. And then we have a corresponding angle theta. So how can we talk about points in polar coordinates and in Cartesian coordinates? How do we translate from one to the other? Well, naturally, we're going to use trigonometry. So, for example, from trigonometry, we know the cosine of theta is equal to x divided by r. And if we multiply both sides of that by r, we get x is equal to r cosine of theta. Likewise, sine of theta is equal to y divided by r, and multiplying both sides by r gives us y equals r sine of theta. And so that's where these two equations come from. But we also know the Pythagorean theorem guarantees that x squared plus y squared is always equal to r squared. And furthermore, tangent of theta, by definition, is y divided by x. So if we're going to convert from polar to rectangular coordinates or from rectangular coordinates to polar coordinates, we may or may not use some of these equations, but you will find sometimes these equations are extraordinarily helpful. So let's go ahead and convert the point 2 pi over 3 from polar to Cartesian coordinates. So when we have the point 2 pi over 3, please understand that r equals 2 and theta equals pi over 3. Now to do this, you don't actually need to draw a graph. You could just use the formulas. But I find that drawing a graph really enhances the understanding of the relationship between these two coordinate systems. So let's go ahead and sketch a graph, and then we'll do the conversion. So first I'm going to draw the angle pi over 3, which I know is in the first quadrant. It's the same as 60 degrees, right? So pi over 3 looks something like this. And then we are 2 units from the pole. So to show that, I'm just going to put a point here, and I'm going to label this as 2 units. Now what I can do is make a right triangle, and then I'll call this side x, and I'll call this side y, and then we just need to solve for x and y. Now once again, we can use trigonometry to do this. I could say the cosine of pi over 3 is equal to x divided by 2 Therefore, x is equal to 2 times the cosine of pi over 3. And then we just need to know what is the cosine of pi over 3. Well, it's a special angle, and it turns out the cosine of pi over 3 is 1/2, and 2 times 1/2 is 1. Also, sine of pi over 3 is equal to y divided by 2, or y is equal to 2 times the sine of pi over 3. And this is 2 times the square root of 3 divided by 2, which is the square root of 3. And so now we have the x-coordinate is 1, the y-coordinate is radical 3. So in Cartesian coordinates, or in rectangular coordinates, we have the point 1 square root of 3. Now, of course, we could have done this problem by simply recognizing that these formulas will convert our r and theta into x and y. And so we could have said directly, since x is equal to r times the cosine of theta, in this problem that's going to be 2 cosine of pi over 3, which is 2 times 1/2, which is 1. And likewise, y would be r times the sine of theta, which is 2 times the sine of pi over 3, which equals 2 times the square root of 3 over 2, which is radical 3. And then in rectangular coordinates, we have the point 1 radical 3. So no picture is required to do this, but again, I think it's good to draw the picture to help enhance your understanding when you are first learning about the polar coordinate system. Next, we want to take the point in Cartesian coordinates, 1, -1, and write it in terms of polar coordinates. So again, I'll do a graph here just to enhance our understanding. So here's our x-axis, y-axis. If we have the point 1, -1, that is going to correspond to this point here. And then what we need to do is find the corresponding value of r and theta. So to do this, again, what I like to do is just draw a triangle. And we know that this is 1 and this is -1. And then I can solve for r because we know that r squared is equal to x squared plus y squared. And so r squared is 1 squared plus -1 squared. And of course, this is equal to 2. And then r will be plus or minus the square root of 2. Now, typically, we're going to choose r to be the positive value. Of course, we could choose the negative. We'll talk about that in a minute. But if I choose r equals positive radical 2, now I need to know what is the associated value of theta that corresponds to this. So for this one, you could say that tangent of theta is equal to -1 divided by 1, which is -1. And then you could find the reference angle for that, which we should know is 45 degrees, or pi over 4. Now, when I say reference angle, of course, I'm talking about this angle here. But that's not actually theta. Theta is the angle from the polar axis all the way around to this angle. So if this angle here is pi over 4, and it would actually be negative pi over 4 as an angle, but as a reference angle, it's always a positive quantity. So if this is pi over 4, then from here to here would be the angle 2 pi minus pi over 4, and that would give us 7 pi over 4. So if r equals radical 2, theta equals 7 pi over 4. But again, remember, there's infinitely many answers for theta. Another value for theta I could use would be to take the angle 7 pi over 4 and add a whole revolution to it. Or I can take that angle 7 pi over 4 and add 2 revolutions to it, right? Or I could take that angle 7 pi over 4 and subtract a full revolution from it. And all of these are going to produce coterminal angles with 7 pi over 4. So for example, here we would get 15 pi over 4. Here we would get 23 pi over 4. And here we would have negative pi over 4. All of these angles could go with r equals radical 2. So all of these are polar coordinates that would coincide with the given Cartesian coordinates. And so any one of these points here would be polar coordinates for the given Cartesian coordinates. Now let's talk about if we had chosen r is equal to negative radical 2. How would that change things? Well, remember, when r is negative, you go in the opposite direction of your theta. So if we want to end up down here, if r is negative, our angle would have to be in this quadrant over here. Okay? So what angle would that be? Well, again, we know this reference angle right here is pi over 4. So the angle from here to here would be 3 pi over 4. So think about that for a minute. If we go to 3 pi over 4, which is this angle here, but then we have negative radical 2, we're going to go in the opposite direction, radical 2 units. Okay? So theta here would be 3 pi over 4. Or I can do the same thing. I can add revolutions to that. So I could take 3 pi over 4 plus 2 pi, which would be 11 pi over 4, etc., etc. So some examples of points in polar coordinates, some other points in polar coordinates, which would also coincide with the point 1, negative 1, would be these points here. And again, there are infinitely many here, so we are just listing a few. Next, let's talk about graphing curves from polar equations. So if you get the equation r equals 2, what would that curve look like when you graph it? So when we say r equals 2, that means that theta can be anything because theta is not a part of the equation. So for example, what if theta is 0 and r equals 2? Well, 0 is this angle right here, and r equals 2 would be this point. What if theta is pi over 4 and r is still 2? Well, again, pi over 4 is right here, and then r equals 2 would correspond to this point right here. Let's do one more. What if theta is pi over 2? Well, r is still 2. Pi over 2 is this angle, and r equals 2 coincides with this point right here. So you see what happens is you're always going to be 2 units from the pole. And of course, this gives us the graph of a circle. How do we sketch the polar curve theta equals 1? So again, when we say theta equals 1, r is not a part of this equation, so r can be anything, meaning r could be positive, r could be negative, etc. So what is theta equals 1? Well, 1 means 1 radian, and 1 radian is approximately 57 degrees, just for reference. So theta equals 1 is an angle right around in here somewhere. So let's go ahead and graph that angle. So this is the angle theta equals 1. And of course, we could carry it on in the other direction, right? Because if r is negative, we would end up down here somewhere. And actually, that line is the graph of theta equals 1. So let's think about that. If theta is 1 and r is 1, then you are going to go out 1 unit on that angle. If theta equals 1 and r equals 2, you're going to go out 2 units on that angle. If r is 3, you'll go out 3 units. Or if r is 2.5, you'll go out 2.5 units. And so if we fill in all the possible positive values for r, you end up getting this entire line. But r could also be negative. What if r is negative 1? Then you would still go in this direction for the angle, but when you get r equals negative 1, you have to travel in the opposite direction 1 unit. And if r were equal to negative 2, you would go in the opposite direction 2 units. and all those negative r values would end up filling in this side of the line. So theta equals 1 is just a line through the origin, or through the pole, and then the angle here corresponds to 1 radian. And I realize this is kind of a strange angle. We're used to angles like pi over 6 and pi over 3, but we can get angles like theta equals 1. Next, let's sketch the curve with the polar equation r equals 2 times the cosine of theta. And then let's find a Cartesian equation for this curve. So this is the first example where we have an equation involving both r and theta. R is equal to 2 times the cosine of theta. So for this, what I want to do is make a table of values. And I'm actually going to put r here and theta here, because points are given in that order, r, theta. But then when we plug numbers in, we're going to choose values of theta to plug in, and that will determine the value of r. And we'll start with just some basic values, like let's use theta equals 0, pi over 2, pi, 3 pi over 2, and finally 2 pi. So let's go ahead and plug these in. If theta is equal to 0, r is going to be 2 times the cosine of 0. Cosine of 0 is 1, and so that's 2 times 1, which is 2. If theta equals pi over 2, r will be 2 times the cosine of pi over 2. Cosine of pi over 2 is 0. If theta equals pi, r is 2 times the cosine of pi, which is 2 times negative 1, which is negative 2. And let's go ahead and sketch what we have here. So when theta equals 0, r equals 2. That's this point right here. Okay, here's theta equals 0, and then r equals 2. And then when theta equals pi over 2, which is this angle, r is 0. So we're all the way back to the origin. And then next, when theta is pi, which is over here, r is negative 2, which means we go in the other direction 2 units, which is back to this point here. So it seems like we're already back to the point where we started. So I don't think we need to plug in any additional points here. What we need to do is plug in some points in between. So for example, let's plug in pi over 3. If we plug in pi over 3, r is going to be 2 times the cosine of pi over 3. Cosine of pi over 3 is 1/2. 2 times 1/2 is 1. So at pi over 3, which is this angle right here, we are out a distance of 1 unit. Okay, now what about another angle? How about 2 pi over 3? If theta is 2 pi over 3, r is going to be 2 times the cosine of 2 pi over 3. That's 2 times negative 1/2, which is negative 1. So if we go to 2 pi over 3, which is this angle here, we are going to travel in the opposite direction, 1 unit, which puts us down here. Okay, so when you sketch out these points, we're going from here to here to here to here. I still don't feel confident about what that shape is, so I need to plug in a few additional points. What if we plug in pi over 4? R is going to be 2 times the cosine of pi over 4, and this will be 2 times the square root of 2 over 2, which is the square root of 2. Oops, and I have that backwards here. This is pi over 4, and this is square root of 2. So at pi over 4, which is this angle right here, r is radical 2, which is 1.4, and 1.4 is right about there. So let's put that point down. Now, if you plug in 3 pi over 4, you will find that you get negative radical 2, which will be a mirror image down here. If you plug in pi over 6, you will end up getting radical 3, which is about 1.7. And then you'll get a point down here just the same. And when you start plugging in more points, you start to see that the shape of this curve appears to be maybe a circle. All right, so now what we're going to do is the second part of this problem, which is finding a Cartesian equation for this curve. And when we do that, you will see indeed it is a circle. So to convert this into a Cartesian equation, let's remember that x is equal to r cosine of theta. And since that is the case, we can make a substitution. If we solve for cosine of theta, we know cosine is x divided by r. So I can put x divided by r in for cosine of theta. If I do that, I get r is equal to 2 times x divided by r. Now this is a strange place to be because this is neither a Cartesian equation nor a polar equation because we have both x's and r's. So we're halfway through the process of converting it. Next, I'm going to multiply by r on both sides. That will cancel out the r's here, and we end up getting r squared is equal to 2x. And then we're going to remember that r squared is equal to x squared plus y squared. And so the Cartesian equation is x squared plus y squared is equal to 2x. Now the question is, do you recognize that this is the equation of a circle? Maybe not, right? So let's convert this into a more recognizable form. If I subtract 2x from both sides, we get this. And then I can complete the square here by adding 1 to both sides. And then if I factor, this becomes x minus 1 squared plus y squared is equal to 1. And this is definitely a circle. The center of this circle is going to be 1, 0. And the radius of this circle is the square root of this number. And of course, the square root of 1 is 1. So now if we go back to our graph, you can see this is indeed what we have. The center of the circle is at the point 1, 0, which is right there. And the radius is 1 unit. So in all directions from here, this is 1 unit. Okay? And so you can see that we do indeed have a circle. Lastly, let's sketch the curve of r equals 1 plus the sine of theta. So for this one, once again, we are going to make a table of values with r's and thetas. And I'm going to plug in these standard values. So let's plug in 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now it's likely you'll need to use additional angles, but these are our main quadrantal angles. And we always want to plug those in when doing a graph. So when theta is 0, r is going to be 1 plus the sine of 0. Sine of 0 is 0, and so in this case, r would just be 1. When theta is pi over 2, sine of pi over 2 is 1, and so r is going to be 1 plus 1, which is 2. When theta is pi, sine of pi is 0, so r will be 1 plus 0, which is 1. If theta is 3 pi over 2, the sine of 3 pi over 2 is negative 1, and 1 plus negative 1 is 0. And finally, when you plug in 2 pi, sine of 2 pi is 0, so r will be 1 plus 0, which is 1. So when theta is 0, r is equal to 1. When theta is pi over 2, r is equal to 2. When theta is pi, r equals 1. When theta is 3 pi over 2, r is 0. And when theta is 2 pi, r is 1 yet again. Now, again, this is not enough to sketch a curve. We don't really know how this goes through these 4 points. So we need to plug in some points in between. So I've plugged in a few additional values for theta. Starting with theta is pi over 6, r is going to be 3 divided by 2, which is 1.5. So that's going to be a point right here. When theta is pi over 4, r is 1.7. So pi over 4 is this angle here. 1.7 is right about there. At pi over 3, we're at 1.86. Now, if you were to plug in angles on the other side, over here in the second quadrant, you would find that you would get these same values here. So what I'm saying here is that at 2 pi over 3, we will have r equals 1.86. At pi over 4, we will have r equals 1.7, 3 pi over 4. And at 5 pi over 6, we will have r equals 1.5. And so you can see that we're starting to trace something like this. It almost looks like a circle, but it's not quite a circle. If you plug in some angles down here in the third quadrant, so for example, 7 pi over 6, you will find that r is 1/2. So 7 pi over 6 gives us r equals 1/2. 1/2 is right about there. And then at 4 pi over 3, we have 0.14, which barely registers. So what's happening is when you come around here, it's going into the middle. And if you continue that on the other side, you get a mirror image over here. And this shape is called a cardioid. And the reason it's called a cardioid is it kind of looks like a heart. All right, so sketching curves in polar coordinates is challenging because we're not used to it. You will find when you first start doing this that you will have to plug in lots of values of theta to find lots of points on the curve to help you graph in the beginning. But as time goes on, you will begin to get used to it and it will get easier. And that concludes this video lesson.